In this video, I'm gonna show you how the potential changes as you move around a loop. And I will use Kirchhoff's loop rule and what I know about potential. So I used this example before, and we have done this surface charge distribution around this kind of circuit. We have looked at the electric fields. In this case, I'm just drawing directly the electric fields inside the wires. Oh, and I forgot. Also, I need to draw the electric field inside the battery as well. It will be pointing that way. And these white arrows represent the electric field around the circuit. Now, you have seen this before. I used Kirchhoff's loop rule and I wrote all of that. What I have here is a graph where the horizontal axis is the point on the circuit. And if you notice, I start from point 1 and then 2, 3, 4, 5, 6, 7, 8. And I go back to 1 because when I apply Kirchhoff's loop rule, I need to end up back at the same point. And on the y-axis, I will be plotting the potential. Now, I do want to mention, when you when you measure potential, you're actually measuring potential difference. You're always measuring potential difference. There is no way you can ever measure the potential just at a single point. It is always a potential difference. Now, what I'm going to do though, I will just make the potential at 1 to be at 0. Okay, I can set the 0 wherever I want. As I said, I measure potential differences anyway, so I can make the 0 to be anywhere. And I'm going to make point 1 to have a potential of 0. And then when I do the measurement, V2 minus V1, I'm going to see whether it's going to go up or down. All right. Now, I want to remind you one more thing before I start with this process. I want to remind you, in the past, when we worked with potential, we saw that if we move in the same direction as the electric field, then the potential decreases. If we move perpendicular to the electric field, the potential stays constant. And if I move in a direction that is opposite to the electric field direction, then the potential increases. I'm going to be using this. Now, for the first term, okay, V2 minus V1, what does that tell me? I start from 1, okay, that's the initial. I start from 1 and I go to 2. That means I am moving to the right to go from 1 to 2. I go to the right, but the electric field points to the left. I am moving in a direction opposite to the electric field, and that means the potential will increase. Let's do it. I'm gonna show here that I have an increase in the potential when I go from 1 to 2. There you go. I got an increase in the potential. Now, when I go from 2 to 3, I go down and the electric field goes up. I am again moving in a direction that is opposite to the direction of the electric field. And from 3 to 4, same thing. Now, here's the thing. Something changes when you go from 4 to 5. The electric field inside the thin part of the wire is much greater than the electric field that you had in the thick part of the wire. If you don't remember that, I do recommend that you go back to the surface charges and you review this. It is important to know that. The electric field in this thin part of the wire is much greater than the electric field that I had so far. Now, what that means is that the potential will increase, but it will increase more than what it did before. So this is what I get when I go from 4 to 5. And 5 to 6, same thing as before. I do have an increase, but a small one, because the electric field is not that great. And from 6 to 7 and 7 to 8, same thing. Okay, so I was from 6 to 7, and then from 7 to 8, the same thing. Now look at this. Now what I'm going to do, I'm going to go from 8 to 1. And if you remember back in that video that I talked about the surface charges, I found that the electric field inside the battery is great. Now look at this. The electric field inside the battery points to the right, and when I go from 8 to 1, I'm also moving to the right. If I'm moving in the same direction as the electric field, the potential decreases. And in fact, if I go here and I take a look at Kirchhoff's loop rule, I know that when I go back to the same point, I need to have a potential change of 0. To have a potential change of 0, I need to go back to where I was at the beginning. And at the beginning, I was at 0 because I started from this point. So this graph is telling you, essentially, it is a graphical representation of Kirchhoff's loop rule. You start from this number for potential, you will end up at the same number if you go around a closed loop. Now, this graph is also telling us some other things, and I can make a note of those as well. What is it telling us? If that the change in the potential across the battery is great. Okay, your potential changes a lot when you move across the battery. Now, if you remember back then when I talked about surface charges here, I told you that this is a simple model of a resistor. So this graph also shows you that you have a significant change in the potential when you move across the resistor. And this part and all of these sections, these are your wires. Okay, so these are your wires, the ones that you use to connect the resistor to the battery with the alligator clips and so on. Okay, so this is a graphical representation of how the potential changes, and you can see the effect that different parts of the circuit have on the potential.